back to Tuesday morning, May the 26th. We are rapidly coming towards the end of this unit. We have a couple more topics to talk about. Today we're going to continue our discussion about induced current, and then we'll get into an application of that, and then we'll be done. And again, you can expect a test by the end of this week on it. Before we get into what we want to cover today, let me share with you a verse of the day today. Yesterday, we looked at a verse from John, and today we want to continue in John again. This is Jesus speaking. He says in John 15, verse 13, where he says, "Greater love has no one than this, to lay down one's life for one's friends." And so again, just a reminder to make sure that you love one another, and not just in your own families, but to love those around you in whatever context you're in. Again, the greatest commandment is to love God and love others. And so I just want to encourage you to do that today as well. All right, so today we want to talk about the direction of the induced current. In our last lesson, we talked about the magnitude of the induced current and how magnitude was determined by a bunch of different things, including the number of windings, wrappings of a coil, the strength of the magnetic field, how fast things were changing, and so forth. And so today we want to look at the direction. How is the direction of induced current formed? All right, and so what I've got here is Lenz, a scientist by the name of Lenz in the mid-1800s, 1834 to be exact, developed Lenz's law for the direction. And he did it through experimentation and by making some initial assumptions and then testing them and then refining them. And then he came up with this law, which works quite well. And so here's the law. I'll read it. It's a little confusing to just look at it and read it. And then we'll describe it with these diagrams and hopefully it'll make sense. So Lenz's law says an induced current flows in such a direction that the induced field it creates opposes the action of the inducing field. So there's a lot of inducing fields going on there, but what he's basically saying is that when we induce a current, let's say we had a magnet and a coil, and we plunged the magnet into the coil, okay? What's happening there is we're inducing a current, and that induced current in the solenoid will induce a magnetic field. All right, so by inducing current, we're also inducing a magnetic field. And so Lenz is saying that the inducing field, the one that's causing the induced current, okay, and then the induced field, he's saying that induced field will be in such a way so that it opposes the motion of the field that was doing the inducing. And again, very complicated wording. Well, let's do a diagram and I'll see if I can make this work for you in your heads. All right, so here I've got a diagram. I've got a solenoid here, and I've got a bar magnet here with its north pole closest to it. Okay? What Lenz is saying is that if I take this bar magnet and I move it into the solenoid, okay? If I do that, it's going to induce a current. And the direction of that current is going to produce a magnetic field around this solenoid. Remember, we talked about the magnetic field around a solenoid and how it looks very much like the field of a bar magnet, okay, with a north and a south pole. Okay, it's going to induce a current in here, and that current is going to induce a magnetic field. The magnetic field that it's induced here will be in such a way that it opposes this motion. All right, so in order to oppose this motion, okay, we again have to go back to magnetic theory and recognize that like poles repel, whereas opposite poles attract. All right, so what that means is if I'm pushing in this north pole to oppose that motion, I need a north pole here so that they are repelling one another. If this was a south pole, it would be attracting it in, and it wouldn't be opposing, it would be helping it out. All right, so I need the current to flow in such a direction here, or the current will flow in such a direction here, that a north pole is created here. And this is where we have to use our right-hand rule again. And again, the right-hand rule says that if I wrap my fingers around the coil in the direction of the current, my thumb will point to the North Pole. Well, now if I know my North Pole has to be here, I'm going to put my thumb there first, and then which way do my fingers wrap around? Well, in this case, they wrap around the back first, and then to the front. Okay, so this current would go this way, which goes around the back, and then comes across the front this way. And that would create a magnetic field around here where the North Pole is here. And that would then oppose this motion. All right? Now, let's change this up. Let's say, I'm going to erase these, put them, leave them like that, and I'm going to erase this. What happens now if instead of pushing this in, I'm going to pull it away? If I'm now pulling it away from the solenoid, again, it's still going to create a magnetic field that looks like this. All right, but now that magnetic field has to be, again, in such a direction that it opposes this motion. So to oppose pulling out a North Pole, this is going to be needs to be a South Pole, right? The South Pole here will mean it's attracting it in, making it harder to pull that out, okay? Opposing that motion. All right, so if I'm going to pull this out, this has to become this South Pole. And again, if that's the South Pole, the other side's the North Pole. And I'm going to use my right-hand rule, which says to put my thumb toward the North Pole. And which way do my fingers wrap around? Well, now they come across the front and wrap around the back. I know it's really hard for you to see. Okay, but it's going to go across the front and then down the back. Okay, so it's alternated, right? When we pushed it in, the current was going around the back and then out the front. Pulling it away, it's going across the front and around the back. All right, in opposite directions. So again, just like Faraday said that if he could open and close that switch, he could create an alternating current in the secondary coil. Here too, by pushing this in and out, we can create an alternating current in this scenario. Okay, we're going to do one more over here with this diagram. Okay, and now this time, so let's take a South Pole here, and let's push it in. All right, so if I'm going to take a South Pole of a bar magnet and push it into my coil, the field that gets produced around the solenoid, okay, it will be produced there, and it will have to be in such a way that I get a South Pole here, right? Again, south has to repel south. It's pushing in, and we want to oppose that motion. Okay, so this would have to become the South Pole. Okay, and this will become the North Pole. So again, I take my right-hand rule. Make sure you use your right hand. The number of people I've seen use their left hand for this is astonishing. Use your right hand. Okay, put your thumb to the North Pole and see which way your fingers go. And they have to wrap around the back. So they come across the front, and then they wrap around the back. Okay, so across the front, wrap around the back. All right, so that's the direction the current would be going. And again, if I were to pull this out, then everything gets reversed. If I'm pulling it out, this will become a North Pole, and the current would alternate to the other direction. All right, so that's the way that works. And that's all we want to cover today. It is a little bit confusing. So what I'm going to do for you is I'm going to photocopy some sample problems from the textbook again, and they're exactly like this. They give you a diagram, and they say determine the direction of the current. Okay, and so there's a couple of sample problems that you can read through, and then there is one question, but it's A, B, C, D. 4 of these situations where you need to determine the direction of the current. All right, and then that's it for today. Tomorrow we're going to start talking. I was going to talk one more thing though. Okay. So again, with this allows us to then create generators, okay? Electric current generators. And we use generators all the time. All of our electricity in Manitoba is done by generators. So I've created a little loop of a wire here, and I don't know if you're going to be able to see this or not, But if I take this loop and I rotate it, okay, this way, I've got obviously a rotating loop of wire. If I were to create a magnetic field, so if I had a north pole here and a south pole here and I was rotating this through a magnetic field, what you would see is that as it goes through one way, okay, I get a current flowing in one direction, and as it continues across to the other side, it will then create current in the other direction. And again, that's how it works, because now we've got a wire moving through a magnetic field, okay, where one side's moving down through it, the other side's moving up through it, which is going to create current. And then when it comes around, it's going to go through again, it's going to create current in the opposite direction. And so by spinning a conductor through a magnetic field, we can induce an alternating current, and that's why we use wind. If you've ever been out in southwestern Manitoba, in the Altona area, etc., you can see the big windmills. If you head north, even as far as Pinawa, you can see the hydroelectric dams, which is water, using water to spin the generator and thereby creating a current electricity that we can then transport to the places where we need it. And so that's the basis for generators. All right, when we come back tomorrow, we're going to be looking at transformers. And again, transformers are what allow us to take the electrical energy from where we generate it to where we need it. And so we're going to look at that, and there are a couple of formulas that we'll look at there. And that'll be the last thing we cover in this unit. And then we'll be getting ready for our test. All right, have a great day. Look for your assignment on Connect, and we'll see you tomorrow.